All right, we're going to talk about gases and stoichiometry. Basically, this is just more stoichiometry problems, but now, since we have the gas law at our disposal, means we could find the amount of gas that was going to be used up or produced, say, in terms of its pressure and volume, rather than maybe its mass, which we might have done before. Okay, first thing I'm going to do is tell you for probably the 27th time that you can do every single stoichiometry problem from the same general framework. Okay. So you want to recognize that you're doing a reaction stoichiometry problem because there are things reacting and because the question is asking you how much of something is involved in the reaction, right? Then next step, make sure you have a balanced chemical equation for your reaction. That chemical equation relates the numbers of moles of things just like it always does, okay? The gas law is going to be just another route to or from moles, right? So with the gas law, if I know pressure, volume, and temperature, I can get moles. If I know moles and I know two of those three things, I can find the third one, right? So if I know how many moles of a gas are formed and I know the pressure and temperature, then I could find out what its volume would be, for example, right? What this really does is it's going to take a gas law problem and kind of staple it on to the beginning or the end of a stoichiometry problem. Right? So if you think about your stoichiometry problem in terms of just saying, I take stuff I know, I turn it into moles, I do things in moles, then I turn the answer into the format I want, you can still do that. It just says now the gas law is another way that you can get information converted into moles or out from moles. Just like when we took up solutions, we said, well, molarity and volume will get you moles. Well, now pressure, volume, and temperature for a gas will also get you moles. That's the whole idea. This video is mainly a couple of examples. The first one is straightforward, related again to a demonstration that I did some number of videos back in which I dissolved magnesium, or I didn't, I watched the video of people dissolving magnesium and hydrochloric acid, okay? Ordinarily, I would do that in the classroom, but that's not how things work right now because I don't have a chemical stockroom here in my home. So magnesium dissolves in hydrochloric acid. It forms hydrogen gas when it does that. What I've written down there is actually the net ionic equation for that reaction, just as a reminder about those, right? So in that format, that equation for that description will bother some of you because you'll be saying right now, there's no HCl in that equation. How is it the equation for dissolving magnesium in HCl? To see that, we have to remember that when my HCl goes in the water, when I dissolve the HCl in water, what do I get? Strong acid, so I get H3O plus, and I get chloride ions, right? So the H3O plus that's in here, that's where, that's coming from the HCl, right? That top equation says I get 1 mole of H3O plus for 1 mole of HCl, so effectively I'm going to use the moles of HCl, or I would use the moles of HCl like the moles of H3O plus. I'm looking down at the question now and I realize it says I have excess HCl, so I don't even have to think about the moles of HCl. I just have to realize that's an okay equation, an okay reaction for describing this, right? My hydrogen gas is over here, and the question is going to ask me to find what's the volume of hydrogen at 25 degrees C and 1 atmosphere, okay? So think about the end of the problem. The last step says, I want to know volume when I know pressure and temperature, right? So your last step is going to be V equal to nRT over P. Right now, you know P and you know T and you always know R. So that says what we have to do from the rest of the problem is find N. Okay, so now I have a question that says when I dissolve 2 grams of magnesium in excess hydrochloric acid, how many moles of H2 do I form? That's not that hard of a problem, so let's do it. Okay, so the first step is going to be to get moles of hydrogen. This is the thing I know, right? I know that 2 grams of magnesium are going to dissolve because it said I had excess HCl, so 2 grams of magnesium. I'm going to turn that into moles. This is 24.3 is the molar mass of magnesium. You'd look that one up. My equation tells me that 1 mole of magnesium makes me 1 mole of H2, so my stoichiometry is friendly. And if I multiply that out, that tells me I have about 0.0823, it says in my notes, moles of hydrogen. That's how much I formed. Then I have a gas law problem, right? The gas law problem just says, now I know N, and I know T, and I know P. So my last step is to find volume, which is nRT over P from the gas law. And I just put in the numbers I've got. So I put in 0.0823 moles. There's a strange little coincidence here because I'm going to put in R in liters and atmospheres, which means I'm also going to put 0.082 there. My temperature is up here, 25 degrees C becomes 298 Kelvin. And then on the bottom, I'm going to go in atmospheres, and I just have 1 atmosphere pressure. My notes claim that the answer here should be about 2 liters. And gosh, if you remember when I played a little bit of the video of that demonstration, this is about how much magnesium was in those things, and that's roughly the size that the balloon blew up to, give or take, when we think about the balloon itself plus the gas that was in the flask, right? So it seems consistent with what we saw when we did that. So again, what we've got here is a stoichiometry problem up here, in this case, followed by a gas law problem. Right? If you look at a problem like this, if you're not sure where to start, good thing to do is to do just sort of how I sort of phrased it there, is to say, well, at the end of the problem, I want to know the volume, and I already know the pressure and the temperature, right? So if you're stuck on a problem like that and you're asking me for help, I'll say, well, what would you need to know to make it easy to find the volume? And most of you would then say, well, if I knew the moles, I could find the volume, because then I would have everything except volume in the gas law, right? So that gets me focused on what I have to get out of the stoichiometry problem. The second sort of use of this, or example of this, I'm going to talk about a little bit, is somewhat more applied. It's the idea of designing airbags for cars, okay? So if you want to design an airbag system for a vehicle, and most vehicles have lots of these nowadays, right? Because there's airbags all over the place in a modern car. What you need to be able to do is you need to be able to generate gas quickly. You have some time on the order of tens of milliseconds generally is the time frame that you have to get your airbag inflated. If you think about it, that's, gosh, the simplest description of this is you're driving at highway speed, say, something happens, something bad happens, your car is suddenly stopped. What you have is about the time it takes your body to travel from the seat to where the steering column is at highway speed when the car is not moving anymore, and that gives you a few milliseconds, okay? We want to fill the bag with something that is not dangerous, right? We don't want to fill the bag with a toxic gas because the gas that goes into the bag is well, it's going to actually come out of the bag deliberately, and it would be likely to make its way out of the bag even if that wasn't part of the design. We have to be able to set the reaction off pretty quickly in response to some sort of impact, okay? There are a variety of ways you could do this. The way that actually is used in all existing systems, I believe is still true, is the chemical generation of the gas, okay? And the most common way to do that is by the decomposition, the somewhat explosive decomposition of sodium azide, which is NaN3, which is a strange looking compound, right? N3 minus is what's known as an azide ion. It's a somewhat obscure polyatomic ion of nitrogen. We can write a simplified equation for this reaction there, which is just the sodium azide decomposes, makes sodium, and makes nitrogen. Okay, good things about this reaction: it's fast, it's easy to set off, it just needs a little bit of a spark, right? So we can have any sort of some kind of spark plug-like device that can be triggered. So your car has what is in this case, I guess, a decelerometer, something that detects that the car has just slowed down dramatically in a way that is not normal, and that's what basically tells it to deploy the airbag, okay? There's probably also some just impact sensors nowadays in modern cars because sensors are pretty cheap and easy to spray around the vehicle, right? Problems with this: as I wrote the reaction there, it's got sodium metal as a product. That would be a bad idea, and I'll show you an equation, a messier equation at the end that has some stuff baked into it to clean up the sodium. The sodium would be bad because, among other things, if your car is in a serious accident, there's a chance that there could be fire around and water might get sprayed on it, and if you have sodium metal there, then that might react with the water and cause further problems, okay? The sodium azide itself is pretty toxic stuff, and so the fact that there are pellets of this in lots and lots of vehicles means there's lots of this ending up in various places that it might be better if it weren't. And so there is ongoing work to try and find alternative reactions all the time. But this one is still in very widespread use, okay? Some of you might be thinking like, well, couldn't you just store gas in the somewhere in the car and just have like a high pressure cylinder that was just going to release the gas, let it expand to blow up the bag? The problem with that is you need a very high pressure to do this, okay? And I'll explain a little bit what we would need to do that, but you would need a very high pressure, and that would put something that essentially is a little bomb of its own just sitting in the steering column of your car and various other places in your car, and the risks of that are greater than the benefits probably. So let's do the calculation from here, okay? I'm going to use some numbers that sometime a long time ago I got from somebody who actually like worked for a car company and had knowledge of this stuff. It says the main airbag, meaning the steering column airbag, typically inflates to a volume around 40 liters at its maximum inflation. It blows up to a pressure a bit above 1 atmosphere, around 1.25, 1.3 atmospheres. It also then deflates rapidly. The bags themselves are porous because you don't want the thing to just turn into a very hard thing of its own, right? You don't want the airbag to act like a basketball once it's inflated. You want it to be sort of a cushion, right? And so the fact that the gas will just gently escape from there means that it will sort of provide a soft landing area, is at least the theory. We're going to find the mass of solid sodium azide we would need to produce enough nitrogen to fill this airbag at 40 liters, 1.3 atmospheres. I'm going to take a temperature of 25 degrees C. In actual fact, the gas produced in that reaction would probably be significantly hotter than that. So we could raise the temperature. We can think about what that would do to our design or our amount we calculate afterwards, okay? Suppose I wanted to do this by expanding the gas. If I wanted to have enough gas to give me 40 liters at 1.3 atmospheres, if I was going to compress that even into a 1 liter can, and a 1 liter can would be a pretty lot to try and like stick in the steering column of a car, right? I'd probably actually have to get it a lot smaller than that. But in a 1 liter can, I'd have to compress my gas to a pressure of about 52 atmospheres, which is 760 pounds per square inch, and trying to like just confine that kind of pressure in your car would put a lot of demands on something that was responsible for making sure that stuff didn't just go off accidentally and let that gas out of there and inflate your airbag without meaning to, right? And so that's the main reason why the approach of just generating the gas chemically is better. As we'll see, we can get a fairly lot of gas out of a fairly small amount of solid. So the first thing I'm going to do is I'm going to start at the back end of the problem. I'm going to figure out how many moles of gas does it take to fill up this airbag with the specs that I gave myself there, right? So N here is going to be PV over RT, right? And so with the numbers I have there, I put in 1.3 atmospheres. I put in 40 liters. I'm still in liters and atmospheres, so I'm sticking with 0.082. Liters, atmospheres, moles, and Kelvin. My temperature, again, converting 25C to 298 K. I put that in there, and that says I need 2.1 moles. And that's how many moles of gas I need, because how did I calculate my moles? I used the ideal gas law, right? So that's the number of moles of gas it's going to take to blow up my airbag, okay? That's not going to be the number of moles of my sodium azide that I need, because now I have to look at the stoichiometry part, the chemical equation for my reaction. Where's my gas coming from? It's coming from this reaction. Okay, look at this reaction. What's the stuff that's inflating the airbag? It's not the solids, it's the nitrogen, right? So that's why my setup here says now my problem is a simple stoichiometry problem. It says how many grams of sodium azide do I need to make 2.1 moles of nitrogen gas, okay? And that's not a hard problem. Start with the thing I know, 2.13 moles of nitrogen. For every 3 moles of nitrogen I want to make, I need 2 moles of my sodium azide. And for the molar mass of that, 1 mole of sodium azide is about 65 grams. because 3 times 14 is 42 for the nitrogen. Sodium is about 23. That gets me to my 65. So that says I need about 92 grams of my sodium azide to be able to generate the gas that will inflate this bag. Okay, 92 grams, that's a bit less than 1/4 of a pound. So if I had that as a solid, that's probably going to be something like the size of, I don't know, like a laundry detergent pellet kind of thing, right? Relatively easy size thing to be able to stick someplace in the steering column. It's not going to take up an enormous amount of room, okay? If I had used a higher temperature, if I had accounted for the fact that when this stuff is decomposing, it's going to be releasing some energy, and so the gas that's formed is going to be warmer, that would actually reduce the amount I needed by a little bit, right? Because if I had a higher temperature, then the number of moles of gas it took to fill that volume at that pressure would be a little bit smaller. So I could maybe have gotten away with a slightly smaller amount, which if I was really responsible for building the airbags, I'd of course, get a rough guess and I would test it and see what happened and figure things out. Let's take a quick look at a more realistic version of this, since you are mostly practical thinking people and all of that. So this is an equation which obviously is much more formidable looking in terms of the chemical formulas that are in there. That's why I did the calculation with that simple one. What does it say? It says I've added some things to the mixture. Instead of just having the sodium azide as a reactant, it's got some silica in there, which is basically sand. It's got some potassium nitrate, okay? The potassium nitrate is there because that helps speed up the reaction. That helps the ignition phase go faster. That gets my reaction to be faster, makes sure I get my bag deployed in time. The silicon dioxide is in here because it's going to scavenge up the sodium, okay? And so you'll see now my sodium, instead of being just written as bare sodium metal, is now in there as this sodium silicate, which would be now a nice and safely inert compound that would not be any sort of threat to have around. The stoichiometry is pretty similar, because if I flip back for a second, the reaction I used was 2 moles of sodium azide to 3 moles of nitrogen. This one, with all the other stuff going on now, is 20 moles to 32 moles. So I only changed that mole ratio by a small amount, right? Obviously, again, if I was the real engineer building this airbag system, I'd get my real thing and I'd do a trial and I'd just see what happened. But the calculations we just did here would be what would help dial us in to make sure we had a reasonable starting amount before we started testing and just setting off lots of little things and seeing how much gas we made.